I'm back with Dr. Jennifer Gardy, a blogger known as Nerd Girl at theglobeandmail.com. She's also a researcher at the BC Centre for Disease Control. As we were talking about before, at the BC Centre for Disease Control, you worked on H1N1, and we were talking about how this open source model of diagnosing and sequencing that the genome helped save lives. Explain how people actually, how did that actually save lives?
I think a lot of it was us being able to anticipate what was coming. I mean, this was the first influenza pandemic in decades, and this was the first that we could actually sequence a virus in real time and watch things unfold. So we had the benefit of years and years and years of influenza research behind us, and we were able to, with genome sequencing, really quickly go in and say, does the virus have mutations that are making it particularly pathogenic? Does it contain mutations that are making it resistant to the antiviral compounds that we're using? And we were basically able to, worldwide, monitor this in real time and assess.
BC was actually sort of central to some of this research.
Yeah, we had at BC CDC we've done some sequencing. We're doing a lot more. We're kind of going back through the archived sequences, but at the time we were sending them into the National Microbiology Laboratory in Winnipeg, and they were doing some really interesting sequencing work there. We were doing some really cool stuff around looking at the effect of seasonal vaccination on people's incidence rate of pandemic H1N1.
So the point of this was that by being able to sequence it so quickly, you were able to create a vaccine for it, right?
Yeah, the vaccine was, the virus was actually sequenced within days of it being first picked up in California, just after it sort of crossed the border from Mexico. And so literally right away, that vaccine strain was being sent to the different manufacturers around the world. So they were able to go in and take a time frame for vaccine production, which is normally quite long. I mean, it starts in February of a given year to have vaccine ready for the fall. They started much later and were able to get the vaccine out much earlier, just because we were able to get the virus sequenced so quickly. And by basically monitoring what was going on in real time with the sequence around the world, we were able to see, this is not turning into something that is really a huge threat. It's not developing antiviral resistance that's spreading throughout the population. It's not developing mutations that we think are going to make it more pathogenic, mutations like you'd see in avian influenza, for example. So we were basically able to keep on top of the threat level and realize that, it wasn't a big deal. It was a big deal, but it wasn't a catastrophic event.
Well, one idea that I know you've put out in the past is this idea of genome surveillance. That as opposed to people come into the hospitals and you sort of watch their numbers and say, oh, there may be something, as happened with the swine flu and avian and all those, you actually would somehow tap into the genome of people in a city. Potentially through sewage.
No, it's a neat idea, actually, and it's been postulated by a couple of people before and discussed over beers with my colleagues and myself many a time. But the idea is that any infectious agent that enters a population is necessarily going to exit that population and exit it through effluent. And so if you were able to come up with a DNA-based surveillance system, maybe a chip that had probes to different infectious agents on it, you could basically install that in the sewage system, and as people's waste flowed over these chips, if there were nucleic acid from a particular pathogen, maybe you're looking for influenza, maybe you're looking for a particular fungal pathogen, maybe you're looking for a bacterium, as the nucleic acid from those pathogens passes over those chips, the DNA would bind to the chip and you'd get a signal and you'd say, oh, we're starting to pick up this in the population. So you'd obviously have to figure out what baseline levels were, take readings for that, look for any cases where you had suddenly a spike in the number of detections of this particular pathogen in the environment. But it could be a really cheap, tractable, and easy way to keep track of us.
Is this science fiction or is this science
It's science fact.
It's science fact. You could actually do that.
Absolutely.
So why isn't it being done?
I think it's just an idea that it's not quite its time yet. The technology exists, but to be able to do it on kind of a citywide level, right now it needs to go past that proof of principle stage.
You can imagine it actually happening someday?
Oh yeah, probably within the next 10 to 20 years, easily. I mean, we've got the technology, it's just a matter of testing it in the field and figuring out the best large-scale implementation. Because people right now, there's research groups around the world that are interested in microbiomes, and these are basically the entire population of microbes, bacteria, viruses, fungi, you name it, that make up a particular ecosystem, and that ecosystem can be the sewer system, it can be a microenvironment, it could be our body, it could be our digestive tract. So people, we're researching this, we have the tools to study these communities, but just to apply those technologies to an actual public health problem, that's really just the next step.
We just have a minute left, and maybe it's not enough time to really address this bigger issue, but I want to ask you very quickly on stem cell research, which has been a politically touchy subject, particularly in the States, under the Bush administration for religious reasons. Embryonic stem cell research was restricted. Was that a boon for Canada to be able to really sort of fill that void? Was there a lot of embryonic work being done in Canada during the Bush administration?
Certainly in every other country except the States, they were able to fill the gap, and I think part of that is due to funding opportunities. I mean, there's money out there from different agencies to do this work, and when you've removed one of the biggest groups of academics in the world from that funding pool, all of a sudden it gets a lot more competitive for the rest of us, who are sometimes edged out by these bigger centers. So
but the Obama administration has lifted the restriction on embryonic stem cell. How has that affected us here in Canada?
I haven't seen any effects so far. I don't work directly with stem cells, but I haven't seen any trickle-down effect so far. I think a lot of people were very resourceful in that time too, and being able to figure out ways around that, and some great stuff came out of that, like the ability to take an adult cell, something that I could harvest one from you right now, and actually turn it back into a stem cell. So you're getting around the whole embryonic issue.
The Vatican has actually funded that kind of research, again, for political and religious reasons.
So yeah, there was some fantastically clever stuff, just from a scientific perspective, some really beautiful work that was done as a result of that. But it's certainly nice to have the ban lifted and put everybody back on the same playing field.
Well, there's so much to talk about science, but we've run out of time. But maybe we can have you back some other time.
I'd love to come back.
Thanks a lot. For more information about Jennifer's work, you can check out her personal website at jennifergardy.com. Have a thought, comment, or issue you want to send us? We'll tell you how in a moment when The Standard returns.